In this video, we look at an example from, say, section 14.5 that would be related to the gradient. And specifically, the example that we're seeing here is more related to what we call the steepest ascent curve. This is an example of a take-home question I've given on Calc 3 exams in the past, and I thought we would take a look at it in this video now. Okay, so what we're seeing here is a temperature function. We've got a function of two variables, so you know that that's going to be some sort of three-dimensional function, t of xy. Okay, you can look at level curves of it, level curves of the temperature function. So looking at all the points at a constant k are what are called the isotherms. Okay, and then what you imagine in this problem, we're looking at imagining an insect, like a little bug, for example. Okay, that is moving around down here in the xy plane, and it is trying to walk along the path that is always leading it to the hottest temperature spot. So the bug is trying to walk in a direction along a path where the temperature is always increasing. Okay, so what we'll do is solve the steepest ascent equations for this example, and we will then look at a plot and see if we can talk about what's happening. Okay, so I'll let you get a moment to write down this problem. I will summarize it on the next page. Okay. What we're looking at, okay, as always, is this key result that the gradient of some function f is perpendicular to the level curves or the level surfaces, depending on if the function is 2D or 3D. It's perpendicular to the contours, aka the contours of the function f. Okay, so what we had in this problem, the insect problem, was a function t of xy. In this case, it's 90 minus 6x squared minus 2y squared. Okay, and the point that we're interested in will have the bug, let's see, they're at the point -1, -1.5 in the xy plane. Okay, and our goal is to find the steepest ascent path, r of t, where r of t is going to be x of t, y of t. It's only 2D, because there are only two variables for your temperature function. Okay, so what we need to do is we need to solve the equations. Dx dt is equal to the partial derivative with respect to x of the temperature function, and to solve dy dt is the derivative of the temperature function with respect to y. Okay, which leads us to solving the differential equation dx dt is equal to minus 12x, and dy dt is equal to minus 4y. Okay, now we go through our calculus here. We'll separate variables. Dx over x is equal to -12 dt, which is going to lead you, after you've integrated both sides, to writing x of t is some constant e to the -12t. By a similar fashion, y of t will be some constant e to the -4t. Okay? Now, we use the fact that we want our insect to travel through the point -1, -1.5. Okay? So if we make our curve r of t and take the x and y of t that we just found by solving those differential equations, you'll get some constant e to the -12t and and some constant e to the negative 4t. And when you look at, say, the easiest time to evaluate, times 0, okay, e to the 0 is 1, so we want our curve at time 0 to go through the point of interest, which means that the the constant c is negative 1 and the constant k is negative 1.5. Okay. So what we can say here is that our curve, the curve we've got, which is called our steepest ascent curve, is equal to negative e to the negative 12t and negative 1.5 e to the negative 4t. That is our curve, r of t, our steepest ascent curve. Okay, let's double check what is important about this curve. Okay, I can draw a sketch of what's important about this curve. We'll do a better picture in mathematics in a second. What's important about this is that this curve is perpendicular to any level curve of the temperature function t of xy. So let's see if I can back that up with a plot. Okay, let's go back up here. We'll look at our temperature function. Okay, we'll do a plot 3D of this temperature function, and you get 90 minus 6 times x squared minus 2 times y squared. And let's plot this from, say, negative 3 to 3, and y from negative 3 to 3. I just want to make sure that the values we pick for x and y encompass the point P there. Okay. So here's your plot of your temperature function, and it's a 3D surface. Okay. If you took that temperature function and cut it with, say, some plane 2, z is equal to 2, let me move this up. How about 60? Okay. Then the curve you get when the blue constant 60 slices the temperature function, you're going to get what's called the 60 isotherm of the temperature. Okay. If you put enough of those contours together, enough of those slices, you will get a contour plot of the temperature function, 90 minus 6 times x squared minus 2 times y squared, and plot again from negative 3 to 3, and plot from y from negative 3 to 3. Here is a plot of all of the isotherms of that temperature function. If you hover over it, you can see that these is the 80 isotherm. So if you cut that surface at a z-plane of 80, all the points along this rim right here, that black oval, are at a temperature of 80. Everything along this bigger oval is at a temperature of 70, and so on. You can hover over and see what the temperatures are at. Okay. Now take a look at the curve we just made. Let's call this plot 1. Okay, and I will hide it. Let's create a second plot, which was our parametric plot of the steepest ascent curve we just found. Negative exponential of negative 12 times t. That's the x entry, negative 1.5 times the exponential of negative 4 times t. Okay, and this is the path that the insect is going to take at time 0 seconds. So let's just say follow the insect for 1 second. Okay, and then you're going to show this plot on top of the contour plots. Okay, there you go. There is the path that the insect is going to take to follow to the to the higher temperatures. Okay. Let me do something here. Let me show more contours. Okay, let's do 20 contours. Okay, and you can see, maybe even draw some more contours. Let's draw 60 contours. Okay. Every time this, maybe that's too many. Let's go to 30. So every time this contour, this curve crosses one of those isotherms, it's going to cross in a perpendicular fashion. There's a right angle right here, a right angle right here, and a right angle right here. Every time you cross. Okay? And that's what makes this curve special. By solving those equations, you're getting the curve of steepest descent. Okay? Now, one thing that's hard to tell here is with this color scheme, if you make the color function a temperature map, then you'll get a sense of where the hot is. Blue is cold, red is hot. So here's where our insect started at the point -1 for x, -1.5 for y. Here's where it started. And if it follows that blue path, you can see it's on a direct course for getting to the hot part. But if it follows exactly this path, it's always going to the steepest part, to the hottest part of the plate. Okay. Any sort of deviation from this path, if you go over, if you use some other path, right, P3. Okay, let's do a parametric plot. Any other path you pick, any other path that, say, maybe goes through the point -1 + 2 times t, and -1.5, say 3 times t. Any other path you pick, okay, and put P3 on here. Any other path you pick, right? They go through the same point over here, but this path, the straight line, went through colder regions than the curved path did. Okay, so if you follow the curved path, the path we're seeing over here on the right-hand side with the exponentials, you went along what was called the steepest descent path. Okay, so this is an example of a function that can be, the differential equations can be written down and solved. In the next video, we'll look at this result that the gradient of a function is always perpendicular to the level curve, and we'll show a more complicated example where the differential equations are harder to solve by hand. So ends this video.